Fuzzy logic is a formal logical framework designed to reason about vagueness and degrees of truth, unlike classical logic, which assumes that there are exactly two truth values, the true and the false. Fuzzy logic allows truth to come in degrees. Statements can be true to a certain extent and false to another extent, typically represented by real numbers between 0 and 1. This makes fuzzy logic especially useful for modeling vague concepts, imprecise information, and gradual transitions that occur in natural language, human reasoning, various philosophical puzzles, and many real-world applications. The motivation for fuzzy logic comes from dissatisfaction with classical logic's strict bivalence when dealing with vague predicates such as tall, heap, hot, or bald. In ordinary language, such predicates admit borderline cases where it seems inappropriate to say that a statement is simply true or false. Some philosophers and logicians argue that classical logic forces an artificial precision onto concepts that are inherently vague. Fuzzy logic offers an alternative by allowing partial truth and thereby capturing the graded nature of many everyday judgments. Fuzzy logic is closely related to many-valued logic, since both reject the classical two-valued framework. However, they are not identical. Many-valued logic typically introduces a fixed finite or infinite set of truth values, such as three-valued or four-valued systems, whereas fuzzy logic usually employs a continuum of truth values, often the entire unit interval. In fuzzy logic, truth values are interpreted as degrees of truth rather than as discrete alternatives. Thus, fuzzy logic can be seen as a special kind of infinitely many-valued logic with a particular semantic interpretation. One of the most influential motivations for fuzzy logic is the so-called Sawright's paradox. The paradox arises from vague predicates and gradual change. For example, a single grain of sand is not a heap, and adding one grain does not seem sufficient to turn a non-heap into a heap. By repeated applications of this reasoning, one is led to the paradoxical conclusion that no number of grains forms a heap. Classical logic struggles with this paradox because it enforces sharp boundaries. Fuzzy logic responds by denying that there is a sharp cut-off point. Instead, a heap may be true to a low degree for small collections of grains and to a higher degree as grains are added. In this way, the paradox is defused by allowing gradual transitions in truth. The Sawright's paradox raises deeper philosophical questions about vagueness. Are there vague predicates, vague objects, or both? Many defenders of fuzzy logic hold that vagueness is primarily a linguistic phenomenon. Predicates are vague because their application conditions admit borderline cases. Others argue that objects themselves may be vague, for example, when it is indeterminate whether a particular part belongs to a cloud or a mountain. Fuzzy logic can be used to model both views, although its most common application concerns vague predicates rather than vague objects. The syntax of fuzzy logic is often similar to that of classical propositional logic. It includes propositional variables, logical connectives such as conjunction, disjunction, and negation, and sometimes implication. The main difference lies not in the formation rules, but in how these connectives are interpreted. In addition to propositional fuzzy logic, there are also predicate versions that include quantifiers and variables, allowing reasoning about individuals and properties. The semantics of fuzzy logic assigns truth values from a continuous scale, typically the unit interval. Logical connectives are interpreted by truth functions that operate on these values. For example, conjunction may be interpreted as the minimum of two truth values and disjunction as the maximum. Other interpretations are also possible, such as product-based semantics. Different choices lead to different fuzzy logics, each with its own theoretical properties. There are several proof methods for fuzzy logic. Some systems use axiomatic proof calculi similar to those of classical logic, but adapted to graded truth. Others employ sequent calculi, or natural deduction systems designed to reflect the underlying semantics. There are also algebraic proof methods based on structures such as MV algebras or residuated lattices. These methods aim to establish whether a formula is derivable or valid relative to a given fuzzy semantics. Propositional fuzzy logic can be extended in many ways. One important extension is fuzzy predicate logic, which adds quantifiers interpreted via suprema and infima over truth degrees. Fuzzy logic can also be combined with modal logic, temporal logic, or epistemic logic, resulting in powerful hybrid systems. Such extensions are especially useful in artificial intelligence, control systems, decision theory, and computational linguistics. From a metalogical perspective, fuzzy logics differ significantly from classical logic. Some fuzzy systems are sound and complete with respect to their semantics, while others sacrifice completeness or compactness. Classical laws, such as the law of excluded middle and the law of non-contradiction, generally fail. However, fuzzy logics remain rigorous formal systems with well-defined syntax, semantics, and proof theory. In fuzzy logic, a sentence may be said to be logically true if and only if it has truth value 1 under all interpretations, logically false if and only if it has truth value 0 under all interpretations, and logically contingent if and only if its truth value varies. Logical consequence is defined in terms of preservation of high degrees of truth. A conclusion follows from the premises if and only if in every interpretation where the premises are sufficiently true, the conclusion is also sufficiently true. In sum, fuzzy logic provides a formal framework for reasoning in contexts where vagueness, gradual change, and imprecision are unavoidable. While controversial and philosophically debated, it offers a systematic and mathematically precise alternative to classical logic with both theoretical significance and wide practical applications.